Hello and welcome to this lecture. In this lecture we shall discuss dimensionality reduction using principal components analysis. Principal components analysis is a widely used statistical technique. So in this lecture we shall attempt to make a very simple description of this concept, and maybe later on we can do a more technical lecture. This one is just to expose anyone who would like to know how principal components analysis works, and we shall approach it mostly from the linear algebra side of the world. There's a lot more you can do from the statistics end, but we shall not look at that. And eventually we shall try to work with the R, the statistical software called R, to illustrate the concept of principal components analysis. So I avoided a lot of mathematics and diagrams and equations, but let's hope that the message gets through. So here we go. Now, first of all, we talk about dimensionality reduction. So sometimes we have a very large data set which with a lot of cases and many measurements. So when we have only two measurements, it's very easy to visualize the data. That is just as simple as drawing it in the XY plane in the two-dimensional space. We can go as far as three variables where we can represent this in a two-dimensional. We can represent this in a three-dimensional space, and we will still be able to visualize the data in some scatter plot. So the assumption here is that the data is numerical. Now, if the variables are so many, then it may not be very easy to visualize the data. So one way to solve this would be to try to throw away some of the variables, but then we wouldn't know which ones are the important ones. We have no way of telling which ones are more important than the others. So this can be a bit risky. We can lose a lot of important information. So we work around this by transforming the data X into a new set of uncorrelated variables, which can be ranked in order of importance, and that way we can throw away some information and be able to tell how much information we are left with. This technique, the technique we will use here is called principal components analysis, and we'll proceed to describe it further. So how does it work? We take the data set X and multiply it by a matrix V. So the question is, how do we get this matrix V? So once we multiply the data set by the matrix V, we get a new transformed set of data T. So X, as we had seen earlier, has M cases. So that is M rows and N variables, where M is supposed to be, we shall take M in this case to be greater than or equal to N. So once we have this transformation, we get a new data set, we call it T, and T will be exactly the same size as X. So what will happen in T is that T will carry the same information. It's just a rotation of the data in X. So we don't lose the information on distance. Any points that were close together before still remain close, and any points that were far apart before will still remain far apart. Now V itself is an orthogonal matrix. It's a square matrix of size n by n, and its columns are just the eigenvectors of the matrix obtained by multiplying the transpose of X by X. Now this matrix, the transpose of X multiplied by X, is just the covariance matrix, assuming that X is centered. In other words, that all the variables have mean equal to 0. If they're not centered, usually you can do that before you do the analysis, and we can do that by a process called scaling. You scale the data. So as said earlier, T is exactly the same size as X, and the entries of T will usually be called scores. And this is the Eigen decomposition of the covariance matrix, that's X transpose X, to get V multiplied by D multiplied by V transpose, where D is a diagonal matrix and the entries in the main diagonal of D are just the eigenvalues of this matrix X transpose X, and they will be ordered in descending order, so that the first one will be the largest, second one will be a little smaller, and so on, keep reducing in size until the last one. And each eigenvector is corresponding to, each eigenvalue rather is corresponding to some eigenvector, and these are just the vectors which are in the which make up the columns of the matrix V. So we shall call these eigenvectors V1 up to Vn the principal components, and its entries of V are called the loadings. Now this ordering is what will help us to determine the order of importance and allow us to throw away some variables in the transformed data without losing a lot of information. So there's a more computationally efficient way to obtain T using a singular value decomposition as opposed to the Eigen decomposition. So this assumes that the matrix X can be factorized into a product of three matrices, that is U, sigma, and V transpose. This V transpose is exactly the same V that we obtained in the earlier calculations. So we still get our V, although we have a few other matrices here, U and sigma. So we are more interested in this V, but this technique of a singular value decomposition is more efficient in computing V or computing T, as we shall see later. So the entries in this matrix sigma are just the square roots of the eigenvalues of the square roots of the eigenvalues of the covariance matrix that we saw earlier, and they are called the singular values of X. So this matrix V will be called the right singular matrix, and the matrix U will be called the left singular matrix. So U comes in handy when computing T, because now if you want to compute T, it will just be the same as multiplying U by sigma, where sigma is a matrix which has many zeros and therefore makes it easier to compute. Sigma has many zeros, it makes this multiplication will be easier than the previous multiplication, where you have to multiply X by V, and that reduces the load on the computer. So how do we reduce the dimension? Since the singular vectors are in some order of importance, we can drop a few and still be able to tell how much information we have retained. We will usually retain the singular values, components that correspond to the large singular values. Most of the time we shall pick only two. In this case we will pick two actually, because we want to be able to represent our data in the two-dimensional space. So we just pick only two principal components, and then we calculate our transformed data T as X multiplied by V2, where V2 will contain the first two columns of V. So now T is a new matrix with a new data set rather, with only two variables, which can still give us a lot of information about the original data set, And not only that, we are now able to plot this in a two-dimensional space. This shall be illustrated in the analysis. So the number of cases will not change. We still have a total of m cases as in the initial dataset, but we will only have two variables and still retain a reasonable amount of information in the initial dataset, and eventually plot this in the two-dimensional space. So we can tell how much information is retained as follows. If we pick the first R principal components, then the information retained is given by the sum of the first R singular values divided by the sum of all the singular values. Then you multiply this by 100. So we'll get some percentage. Usually 95% is good, but we may not always get 95%, and we can still get fairly good insights with lower percentages. So you just have to use your judgment, because what we are doing here is mostly an exploratory venture and looking for patterns. So most of the time, a good number of times rather, we are able to work with only two components with fairly good results, and the two principal components is good because then we are able to plot this in the two-dimensional space and be able to find patterns in the data. So we are going to attempt to apply this technique to the coronavirus data. The data is from this website called worldometers.info, and they update it daily. So the data I'm going to use for the analysis is a little older than what is appearing on the screen. This had already picked the earlier data, and that's what I will use for the analysis. But this is what was there at some point. Maybe even as you see this, the data will have changed on the website. So you see we have several variables: total cases, new cases. So let's count them: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Total of 11 variables. They are quite likely to be correlated, so that's another good thing about principal component analysis. It will give you a new set of variables which are not correlated. We shall not check the correlation in this instance, but they are likely to be correlated variables. Then we have many countries. We only shown a few here. I think there are over 200 countries in the dataset. So you can check this by just going to the website, and you'll be able to look through the tables to figure out how the data is. There's some sections here that were blank. I replaced all of them with zeros, and then there are these some countries don't have data for total tests. I simply omitted those countries from the analysis. And then also we can see UK has missing data here for the total recovered, so that was also omitted from the analysis, as we shall see later. So we shall apply the principal components analysis. So instead of now working with a total of 11 variables, we shall transform the data and only work with 2 new variables. So as mentioned earlier, the data was obtained from the website worldometers.info using LibreOffice Calc. So I just was able to pull it out of the internet using the LibreOffice Calc. Then analysis will be performed using R software. LibreOffice and R are open source, and you can download them for free online. Just search for R or LibreOffice, and you should be able to find them easily online. And there are many YouTube videos on how to download and install the software. You should be able to find this easily. And if you are not familiar with the software, you can just watch, and maybe later on you can try to learn the software and apply it. So we will now move to the demonstration using R. So the data is available on this website, worldometers.info, and you can click on this link, the coronavirus, to see the data for different countries. So there's this link that takes you to the data for different countries. Here we have the data for different countries, and you can see America has the highest number of cases. There are a few blank spaces on the new deaths. I assumed all these are zeros, and I replaced them with zeros in my data table. We also have some countries that do not have data for total tests and tests per 1 million population. So these again will be omitted from the analysis, and we'll also consider only countries that have more than 200 reported cases. So that would be from somewhere around here if it was this data set, but from the one I have, I think it will be a little different. By then I think Kenya was not at 200 yet, the one I picked. So anyway, I picked this data from the website using LibreOffice Calc, which is a spreadsheet. That is this is the spreadsheet. So you simply go to the spreadsheet, click on this sheet, and then you say link to external data, and you put in the website link and wait for the table to show up in this section. But for some reason today it's not working, but this is what I did to get the data. Once I got it, I saved it as a CSV file and imported it into R. So we'll just move on to the R file. So R is here, and the code for the analysis is here as well. So here on the second line, so the code for the analysis is here. Let's clean up everything. Also clean up this part. Okay, I think now we can start. So this first line, we can see, reads the data from the CSV file that I created. You would have to go to here to see the file. That's corona.csv. That's the file that is being imported into R. So the first line does that. Let's run it and see what happens. There. So now we have the first line of code, and we have the data now imported into R. So we can view what is in the data. You can see USA has 560. This is different from what is current in the website because I picked my data a day before, so the values here are different. And even for the day before, I think they were updated later, and they will still look different from what I have in the file. But we'll just work with what I have in the file. We will not refresh the data. So the next line, that's line number 6, we'll assign the data into a new variable called corona1. Then we move on to line number 11, which picks out the missing data, or picks the cases and stores them in this variable called missing data. Picks the cases that are incomplete and have missing data. Then we assign the missing data. First of all, we remove the missing data and assign it to a new variable called P. Then we now move it to a new variable called corona2. We assign P to this new variable corona2, but we add some conditions on the cases. We only consider cases that have total tests that are non-zero, and we also consider countries that have more than 200 reported cases of corona. Then we go on and scale the data. So this command at line number 18 will scale the data, and we store it in a new variable called corona3. So for us to get our matrix of singular vectors and also to obtain the singular values for our data, we run the svd command on our data on line number 21, and this is what it does. So we can get the singular values. It's part of the output of the svd command, and that is obtained on line number 23 and assigned to a variable called sing_c. So I'll just run that. If you want to see what is in the singular values, we can look at the first 6. They are supposed to be 11, I think, in total, but we can look at the first 6 like that. Just put in the command there. So now we can see the first 6 are here. We have 22.7, 13.2, and so on. So the first 2 are fairly big, and that is good news for us, because we just want to use the first 2 singular values and not more than that, because we want to plot our data in 2 dimensions. So let's see how this looks like in a graph. We can plot the cumulative sum of the singular values over the total sum of the singular values, and this will help us see whether picking 2 of them will be enough. So if you look at the graph, we can see the first 2 stop at around 0.6, a little above 0.6, that's about 60%. So the first 2 singular values will cover about 60% of the information in the data, and we can actually do that computation on line number 28. That will give us the amount of information retained by just picking the first 2, and let's see what that will be. Not there. So we go down here and type var what's in this variable. So it's about 62%, just like we see in the graph. It's about 62% of information retained if you pick only the first 2. So at the next line, number 30, we extract the matrix V as discussed in the slides. Also, the matrix V is part of the output of this svd command, the singular value decomposition command. We assign the matrix V to a new variable called v_tr. We also bring the dataset, the scaled data, and assign it to a new variable called x. So now we have x and v, and we are going to transform x using v to get t, our matrix T. So T is transformed, but we only use the first 2 principal components, and therefore we'll get a truncated T which has only 2 columns. Then we are going to plot the 2 columns to be able to visualize the data. So let's run that. Get v. We assign v to v underscore tier. Then we get x. We assign the data to a matrix X. Then we obtain t by multiplying x by v, but only picking the first two columns of v, so that we get a truncated version of t, which is what we need to plot it in a two-dimensional space. So we do that we plot the two columns of t. That's done on line number 37. So after we plot the data, this is what we see. So along the x-axis we have the first principal component, and along the y-axis we have a second principal component. We see there's one country. This must be America all the way on its own, but then we have some 4 countries here which form a cluster. There seem to be a few other clusters. There are 3 countries here which form some cluster. There are another 2 which form a cluster on that end. There are these 2 which seem to be far from the rest. The next plot we shall indicate the names of the countries so that we can figure out what these countries are. Then the majority of the countries are now clustered here on the left, so on. So let's see if we can get a better looking plot, at least with the country names included. Okay, so first of all I will set up this. C1 is a variable now that will store the information about the countries. We shall need this in the plot. I set up t again as a data frame because the next function that we shall use to plot the ggplot requires the data to go in as a data frame. Now we also need to load the library. That will help us use this package ggplot2. So let's load that. That should enable us to run this ggplot. There you go. So this is a new plot now using ggplot, but now with the names of the countries included. So you can see we have a cluster here for Germany, France, Italy and Spain. They seem to have formed a cluster there. Here we have Switzerland, Iceland, Luxembourg and Belgium. They seem to have formed another small cluster here. The USA, as expected, is far on its own because it has a lot of reported cases, and the statistics are much higher than other countries on almost all statistics on the reported cases and the number of deaths and so on. The USA is much higher, so this is expected that USA should be far out on its own. Germany, France, Italy and Spain seem to have similar characteristics. Then the majority, again, you can see, are clustered here. Andorra and San Marino are very low populations, so maybe their statistics may be a little exaggerated. For instance, the number of tests per million may be exaggerated. They have less than I think they have less than 100,000 in terms of population, but you can confirm that. So that's it. we've been able to see how to visualize data that had several variables, and now we're able to see it in 2 dimensions and visualize it in a 2-dimensional plot and be able to pull out any patterns that we see. So it serves a purpose. We've been able to show that you can reduce the dimension of the data and plot it in only 2 dimensions. So thank you, and if you found this useful, please subscribe to our channel, and let's fight the virus.